Hello, so this is going to be a really fun video. I've been wanting to do this video for some time now, and this video is going to be about how we can find a value for the infinite series 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus and so on to infinity. And the surprising thing is that the value of this is equal to pi squared over 6. Now, it's very strange that there is pi squared over 6 into this infinite series. Whenever you see pi, the number pi comes from sines and cosines and angles, so circles and circumferences. So whenever you see pi, you can be sure that there is a sine and a cosine and arctangent lurking somewhere. So let's see what we can do here. So in order to find this sum, I'm going to first write down some facts that I know. So I know that the function sine of x can be expressed as an infinite series itself, and this infinite series is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial minus and so on to infinity. So all the powers are odds, the denominators are odds, and they are factorized. That is, you take the factorial of each of the denominator, and that's sine of x. If you take any angle and you substitute that angle for x here, and you sum a few of these terms, the value is going to converge into the sine of that angle. So this is actually how calculators calculate the sine. So we also know a second fact that we're going to need for this proof of this is that sine of x can also be expressed as not as an infinite series but as an infinite product. So this sine of x is equal to x times, then we have 1 minus x squared over pi squared, then we have again 1 minus x squared over 4 pi squared, then again we have 1 minus x squared over 9 pi squared, and so on. So the pattern here is there's always a 1 here, there's always an x squared here, then on the denominator there is always a pi squared, but the powers here, the numbers on the denominator, they go as 1 and then 1 squared and then 2 squared, which is 4, 3 squared, which is 9, and let's start another term here. So 1 minus x squared over 16 pi squared, and so on to infinity. Now this, if you look here, this is exactly the pattern that we see here. This series can also be written as 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus and so on. And so if we look here, you know, there's something going on here. We just need a spark. We just need a spark so we can close the gap between what we know and what we don't know. So because we can see here that all the powers that we need are here at the bottom, we need a way to extract these powers. We need a way to take these powers and put them somewhere else. We need to add these together and see what we can come up with. So let's see if we can expand these products. Let's see how we would go about expanding this product and seeing what we can get. So let me change the color here and pick a nice color. Let's see this color. So let's see how we can expand this. Let's expand all of the terms that have the x squared in it. So we can take, first we take the first x, and then we multiply this x by this x squared here, Okay, so we get, and we multiply by this term, so we get that this is equal to, so we get a minus sign here, so we get minus x times x squared is x cubed, and in the denominator we have pi squared. So we take this. Now we take the second one, and also because this is an infinite product, we cannot stop here, we have to keep multiplying. So after multiplying x by x squared, we multiply the rest by 1. So then we get this by 1, and then again we take the 1 from here and the 1 from there, and so on. So the final term is going to be x squared over pi squared minus x cubed over pi squared, sorry. So then we take, let's take the next term. So for the next one we multiply x by 1. So x by 1, let me change color here. So we multiply the x by 1. Then on the second term we multiply this by this guy. Then the rest are we multiply by 1, and so on. So for this we get x times 1 is x, times this guy will give us minus x cubed over 4 pi squared, and then we multiply the rest by 1s, and this is the term we get. Now let's switch colors again, and let's see, we do this again one more time. So we take the first x, multiply by the first one, now we multiply by the second one, and the third term we multiply by this guy. So that's gonna give us minus, so we get x times 1 is x, times 1 is x again, and then times minus x squared over 9 pi squared is going to give us x minus x cubed over 9 pi squared. And we do this, and you can see the pattern here. Now we have found the pattern. We can keep doing this to infinity, one term after the other. We multiply the x by all of the ones, and then the last term we take the second term from the factor and multiply the x by that, and then all the others after is going to be the ones. We take the ones, so we form a pattern here. So we can see that this is equal to minus x cubed over pi squared minus x cubed over 4 pi squared, and we can see how this will continue. We can see the pattern here. It's 1 squared, here is 2 squared, here is 3 squared, so the next term is going to be x cubed over 16 pi squared minus, and so on, so on. Now because these products we have, this is not the entire product for the sign, there's an infinite amount of terms. We are just collecting the terms that have x cubed in them. So all the powers from this series are gonna have an odd exponent. We are taking only the exponents that are 3. So we take the first x, multiply by the x squared, and then we take all the other ones. So this is going to give us the x cubed terms. Now because this product is equal to this series, it must be that if we compare coefficients on the x squared x cubed terms, it must be that this entire thing here is equal to this term here. Why? Because we're comparing the coefficients. These two series are exactly the same, so all the coefficients for each power is going to be the same. So this means that this term here, it means that minus x cubed over 3 factorial must be equal to it must be equal to this series here, which is minus x cubed over pi squared minus x cubed over 4 pi squared minus x cubed over 9 pi squared minus, and so on. So in order to compare the coefficients, we can cancel the x cubes, divide both sides by x cubes, and these guys disappear. And then we are left, we also multiply both sides by minus 1, so these guys become pluses. And then finally we're left with the beautiful fact that 1 over 3 factorial, now 3 factorial is 2 times 3, so this is equal to 6, so 1/6 is equal to 1 over pi squared plus 1 over 4 pi squared plus 1 over 9 pi squared plus, and so on. Now if we multiply both sides by pi squared, we get pi squared over 6 is equal to 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus, and so on. So you can see we have our result. This is exactly what we were looking for. We were looking for a way to add all of these terms and get a finite answer. So if you look back here, this is exactly what we were looking for. So this I hope this gives you some impression of what it is like to solve problems in mathematics analytically and creatively. Mathematics is not just about the boring stuff they teach you at school. There's a lot of cool stuff, lots of creative stuff that you can use your mind and your creativity to solve. If you see, we only use two facts here, that the sign of x can be expressed both as an infinite series and an infinite product. Of course, for this proof you have to know ahead of time that this is true, but if you study mathematics and you are used to this, you will no doubt come across these two formulas either by yourself or by reading about it in books. It's very likely that you will come across it by yourself in your own studies. So you just take these two facts, and then you take the simple fact that you can compare coefficients in an infinite series, and you can do sums like this, and you can also do more sums, different sums, not just this one. So I hope you have enjoyed the video, and thank you very much for watching.